Good afternoon. Welcome to recitation session number 7. And we'll start with green functions because that leads right into Green's theorem. Well, and this was developed by a guy, George Green, mathematician, in about the 1830s. And it's a way to solve a differential equation. Okay, subject to boundary conditions. So the general form there is some differential operator on a function is equal to a driving function, a source function. Have you seen this before? Maybe in your DiffyQ class? Okay, so it's the same. We're just starting from what you already know about that. F of x, though, is an unknown function. G of x is the source or driving function. Okay, and L is the differential operator. Okay. Now, if g of x is equal to 0, then it's a homogeneous equation. And an example is the Helmholtz free space wave equation. Laplacian on plus k operating on u is equal to 0. And here the differential operator would be del squared plus k squared. K is a wave vector, or wave number. Now, when we're thinking about Green's functions, or green functions, this is really a response of the differential operator to an impulse. And it's subject to boundary conditions. So, for the Helmholtz equation, we would have del squared plus k squared g and g of r is equal to delta of r. Okay, and this could be displaced from the origin, like we did in our development for the Rayleigh-Sommerfeld equation. We'll leave it like this for now. It's just a little easier to go through. You don't have as many terms to go through. And we're just going to say that an initial choice is g of r is equal to, actually it's, if it's at the origin, we can just say scalar r, e to the minus j k r over 4 pi r. Okay. And as we already said, if we include the time factor here, then e to the minus j k r minus omega t over 4 pi r is an expanding spherical wave. Okay. Now, in order for this to be a solution, we have to show that the differential operator is equal to, or satisfies the impulse function. Or the differential operator on G satisfies the impulse function. So we're going to break that proof into two parts. And first is going to be looking at just the differential operator on 1 over R. And then we're going to apply that result to the equation that we want to show, del squared plus k squared of e to the j k r over minus 4 pi r is equal to a delta function at the origin. Okay, so in spherical coordinates, the Laplacian operating on a scalar function psi is 1 over r squared partial with respect to r squared partial of psi with respect to r plus other terms in phi and theta, but we don't have any of those with the function at the origin as scalar function r. Okay, so we're going to let psi equal 1 over r, and that's equal to the limit as epsilon approaches 0 of 1 over r plus epsilon. So del squared of 1 over r is equal to the limit as epsilon approaches 0 of del squared 1 over r plus epsilon is equal to the limit as epsilon goes to 0 of 1 over r squared partial with respect to r of r squared partial with respect to r of 1 over r plus epsilon. Okay. And then this is equal to, let's see here, what can we do? Well, this is pretty easy partial. It's just a one-dimensional partial. So this is just the limit as epsilon goes to 0 of 1 over r squared partial with respect to r of r squared, and then this partial is just minus, let's see, a minus 1 and then a square there for the denominator, r plus epsilon squared. All right, and I'm going to leave that in that form for now. We're going to come back to it in just a minute. Oh, I'm sorry. Okay. So let's see. In order to show that the differential operator on G is a delta function, we must show that the integral of the delta function dr has a finite value. And so we start with the limit as r approaches infinity, and this carryover from the other equation, limit of epsilon as epsilon approaches 0, just the spherical coordinate integration there, 1 over 2 pi, 0 to pi for theta and phi, and then 0 to r, where r goes to infinity. That's just all the volume of space. And then the differential, or the Laplacian on 1 over r plus epsilon, and then the spherical differential volume, r squared sine theta dr d theta d phi. And now we already worked on that guy a little bit, so we'll substitute him back in, keeping the front limits, and I'm just going to write them as stacked limits here. 0 to 2 pi, and then the integral, from 0 to r. We can go ahead and do theta. We'll do this first. Del squared, I haven't actually substituted in yet the result from over there. I'm just working with the spherical coordinates. dr, and then just the cosine, actually minus cosine of theta evaluated from 0 to pi, and then the d phi. So this is limit as epsilon approaches 0, r approaches infinity, and now just the evaluation of the theta part is 2 integral from 0 to 2 pi, and then the integral from 0 to r of del squared 1 over r plus epsilon r squared dr d phi. Okay, so this is just a 2 pi here with d phi. So limit of epsilon approaches 0, r approaches infinity of the additional 2 pi is 4 pi. And then all we have is the integral with respect to r, 0 to r, and then this integrand here, del squared 1 over r plus epsilon r squared dr. Okay. And continuing that on, I have, now, let's see, now we substitute in our result from the other board. So I still have the limits there. And 0 to r, now substitute in the result, and I have 1 over r squared partial with respect to r of minus r squared over r plus epsilon squared, r squared dr. Of course, the r squareds cancel. And now if I see, do the integration over R, realizing that I'm integrating over dr, and I have a partial of dr. So in the end, what I wind up with is just the value of this function at the limits, but I've got a 0 here at the lower limit and an r at the at the upper limit. So then this works out to just be minus 4 pi limit as r approaches consistent here. Epsilon approaches 0, r approaches infinity of r squared over r plus epsilon squared. And so this is just when epsilon goes to 0, then this expression is just equal to 1. So I have that the integral there is a finite value equal to minus 4 pi. Okay, so that just means that if we integrate the Laplacian of 1 over r over infinity, we have a finite value. Okay, that's one thing that we need. And we also need to show that the limit in r approaches 0 of the Laplacian, again 1 over r plus epsilon, goes to plus or minus infinity. Okay, so to show that, del squared of 1 over r plus epsilon is just using the second derivative there in the call out for the spherical coordinates. I have minus 2 over r plus epsilon squared plus 2 over r plus epsilon cubed. Okay. Now, as the limit, then, as r goes to 0, and don't forget we have the limit for epsilon going to 0 also there, is so that the limit of del squared 1 over r plus epsilon goes to infinity. As you have, as epsilon goes to 0 and r goes to 0, this term goes to infinity, and so does this one. Okay, so that's actually independent of epsilon, because this first term here goes to infinity anyway. Okay, without respect to what epsilon's doing. So our last part of that proof is to show that del squared of 1 over r plus epsilon is equal to 0 for r not equal to 0. So we've got it equal to infinity as r approaches 0, and we've got a finite volume of the function, and now we just need to show that outside of the r equals 0 condition that there's a finite value. So for that one, we kind of repeat what we did up here. The limit as epsilon goes to 0 of del squared 1 over r plus epsilon is equal to the limit as epsilon approaches 0 of minus 2 over r cubed. Okay, and then what do we have here? Plus 2 over r cubed. Okay, so these guys cancel, and we have 0. Okay, so it satisfies a delta function. Okay, so therefore, the Laplacian operating on 1 over r is equal to minus 4 pi delta of r. Okay, so now we want to go back and apply that result to including the complex phase exponential. And just go ahead here. So now we're going to apply the result to psi equal e to the j k r over r. Now for r not equal to 0, del squared of e to the j k r over r plus k squared e to the j k r over r, which included that second term there, is equal to 1 over r squared partial with respect to r of r squared partial with respect to r of e to the j k r over r plus k squared e to the j k r over r. So this is just that same spherical coordinate Laplacian. And so what is that? Well, we've got 1 over r squared out in front, partial with respect to r, and then r squared, and this is just two functions of r multiplied together. So we break that out with our calculus, jk e to the jk r over r for the first part. That's just the partial of r. And then minus the numerator times the partial of the denominator there with the denominator. So that's minus e to the jk r over r squared. And then hanging on here is this k squared e to the j k r over r. Okay, so now to take through the partial, we have an r squared here, so this would be r of j r k for this one, and then just minus e to the j k r for that one. Okay. And now we just take this through. It's pretty simple. We have 1 over r squared. And then, let's see, this first guy would be jk e to the jkr. That's partial with respect to the r. And then multiplied by e to the jkr. And now we take the partial of the exponential. We bring down to jkr, and j times j is minus 1. So we get a minus out in front. K squared r e to the jkr. And then finally the exponential partial here, jkr e to the jkr. And then we have plus k squared e to the jkr over r. All right, so let's look here. Let's see, I think I JK. I think this should not have an R in it. Okay. Yeah, that was a mistake. Sorry. Okay, so we have JK and minus JK. Those guys cancel. And so we have 1 over R squared times minus K squared R e to the JKR. So we have K squared over R e to the JKR. And then we have plus K squared. Let's see, that should be a minus sign there. Plus K squared over R e to the JKR is equal to 0. You know, it's like one of those cartoons you see, the mathematics with the 4 boards of mathematics that equal to 0. Isn't that fantastic? Okay, so that's just saying that, okay, the Laplacian plus K, this is the Helmholtz, right, operating on G outside of the region where R equals 0 is equal to 0. All right, so that should be that way to satisfy the delta function. Okay, I guess it's beauty is in the eye of the beholder here. Okay, so now for R approaching 0, e to the JKR over R, well, if R approaches 0, then the exponent approaches, the argument of the exponent approaches 0, so that's just 1. So this guy approaches 1 over R. And we can apply all of our analysis for 1 over R that we did on the other boards, where the integral over the volume of del squared plus k squared e to the JKR over R over the volume, I'll just write it this way to simplify things, goes to minus 4 pi. And the limit as R goes to 0 of del squared plus k squared of e to the JKR over R goes to infinity. So we've shown, what we've shown is that the differential operator consisting of the Laplacian plus the wave number operating on e to the JKR over R is equal to minus 4 pi delta of R. So what we've shown then, a good choice for our Green's function is minus e to the JKR over 4 pi R. And that's one of the components that we actually did 2 of these, but you can add these linearly. So to help you with your boundary conditions, this is exactly what we did. So this verifies that the Green function actually does satisfy the driving equation. Okay, now what's next is to look at how to apply this in optics with Green's theorem. And that's a little different. So what we'll go through is a derivation of that. Okay. And Green's theorem derives from the Stokes Divergence Theorem. And I won't go through the proof of this. This is something that you should have had in your electromagnetics, either as an undergraduate or as a graduate class, where if we have a volume, guess what? It looks like a kidney bean, with a interior volume V and a surface S and an external normal N. And we have some vector field now that flows through the volume and the surface, and there's no sources or sinks. It's just the vector field there. So this vector field I'm going to call capital psi, and psi has to be well behaved on this. Then we have the divergence theorem, the integral over the surface of psi dotted with this outward facing normal derivative is equal to the volume integral of the divergence of that vector field over the volume. Remember that? It should look familiar to you. All right. So now we're going to let psi be equal to u times the divergence of g, where u and g are arbitrary scalar fields. Okay, and for us, U is the electric field, and G is the Green function. And we're going to also have to remember a vector identity the divergence del dot u partial g, or divergence of g is equal to u Laplacian of g plus divergence of u times divergence of g. Okay. Okay, so all we're going to do is substitute, well, it should be a vector there, the u del g into the divergence theorem. So we have the integral over s of u del g dotted with the normal surface integral is equal to the volume integral of del dot, let's see, u del g. That's just substituting in psi over the volume. Okay. Now, we can use our vector identity here. It's exactly what we have here. So this is equal to the integral over the volume of del dot, let's see, what is it, u del squared g plus del u del g over the volume. Okay, now what we're going to do is do this twice. We're going to reverse u and g. Okay, question?
Did the del dot not go away? That was what point to
Thank you. Very good. Somebody's awake. Okay. Now, what we're going to do is reverse u and g and realize that del g del u is equal to del u del g. Okay, so just reversing there, we have the integral of the surface of g del u dot n hat d squared x is equal to the integral over the volume of g del squared u plus, it could be del g dot u, but I can also write that as del u del g. Okay, and now we just subtract the two equations. Okay, so when we subtract the two equations, we have the integral over the surface of u del g minus g del u dot n hat d squared x is equal to the volume integral of, well, these guys cancel, u del squared g minus g del squared u. And that's what we used in our development of Rayleigh-Sommerfeld. Now, what we did is okay, I've got a few more steps here to get it into our form. This is it, okay? But in class, I brought in this guy, okay, inside to form the normal derivative. So let's do that real quick. It's just one little last step. Okay, so let's just work on one of them. U del g dot n hat. Okay, well, this is the part that produces the vector. It's a gradient, right? So we can write this as u times n hat dot del g. Right? So it's n hat times the divergence of g. And that we wrote in class as u partial g with respect to n. That's that normal derivative where partial with respect to the normal is equal to n hat dot del. Remember that? Probably not. We used it. Yeah.
Sorry, can you go back to this? The left-hand side is scaring me a little bit.
Scaring you?
The second line.
This line?
Yes. How do you go from u del g to g del u?
I just reversed. There are two different equations.
Oh, there are two.
Yeah. All I did was reverse g and u. I didn't say that these were equal. They're not.
I'm sorry. Okay. So they're equation 1 and
Equation 1, yeah. If you want to think about it, this is 1, this is 2, this is 1 minus 2. Sorry. Yeah, sorry. Okay?